Okay, guys, we're starting in with energy changes, reaction rates, and equilibrium in Chapter 6. We're going to do some things today, so with that, we're going to do some demonstrations, and we're going to do some rotations with that. Yes?
Are we doing the other class again, like last time for demonstration?
No, we're doing our own demonstrations.
Oh, like
In here, yeah. Okay, so let's go ahead and get started. This is I think it's a fun unit. It has a lot of stuff in it, but not too tough. And it's not going to let me go forward. How nice of it. Come on. Okay, so again, that sort of tells me what we're going to be doing. So as we get started here, this is the more boring part. You need to have some definitions. So chemical bonds store energy. The lower the potential energy, the more stable they are. If reactions that form products have lower potential energy than the reactants, then they're favored. If they have higher, then they're not favored. So a reaction will not likely take place unless a lot of energy is put into it. And if you remember when we did the bonds, when I showed you the bonds, the single bond, double bond, triple bond, I had somebody up here standing and they shook hands. That single bond was pretty low energy for potential, so it was pretty stable. Double bond, still we had some thing, but it was a little bit more restrictive. It had to have a little bit more energy in there, so the potential was a bit greater. As we got to the triple bond, we had the knee up there. That was very unstable, and it had a lot of potential energy, something that could easily go off. Okay, so it's like a rock at the top of the hill. It has a potential to grow all the way down the hill. And when you let it go, it becomes kinetic energy. If we're down farther on the hill, it has less potential energy because it can't roll as far, so it can't get going as fast. Okay? So as we look at energy and the units of energy, a calorie, which what most of you are familiar with, the calorie that we use in lab is 1,000 times less than a nutritional calorie. A nutritional calorie is actually a kilocalorie. A lab calorie is something that will heat 1 gram of water by 1 degree Celsius. The SI unit for that is joule. And so we have got up there 1 calorie is equal to 4.184 joules. And you need to know the back and forth of that. So calories is the English system, joules is the SI system. And when you see something on the side of a nutritional fact thing that says 25 calories, that's actually 2,500 calories. Okay? Yep. So it would be a kilocalorie. When we do a nutritional calorie, so if we can also say it's way off. Okay, 1 kilocalorie is equal to a big C calorie. That's also known as a kilocalorie. For some reason, my board is off. Yep. I can try anyway. Nope, it's going forward. It's going forward. Okay, I'll go over here. For some reason, that board is off, and I don't know why it's doing that. Okay, right there. I'll have to readjust it for next period. All right, we've got those conversions. They are also on the back of your periodic table, so you can get them from there. Come on. So when we have energy changes in reaction, when molecules come together and react, or bonds are broken in the reactants and reformed for the products. Breaking bonds always requires energy. It just doesn't happen. There's some energy required. To cleave a bond, it takes, for this chlorine, it takes about 58 kilocalories per mole. And you have to add that. When bonds are formed, energy is released. So in other words, like in marriage, if you have a divorce, it takes energy, it takes a lot of stuff, and you have to get 2 places now instead of 1. on the other hand, when you get married, you go from two places to one place, so you can release the energy of one place, keeping one place up. So that's how I keep it straight in my mind. If it works for you, great. If not, you'll want to find another way to remember it. But remember, to break bonds takes energy. To form bonds releases energy. Doesn't want to go forward. Okay, so as we look at bond energies, bond dissociation energies, we use what's called delta H. Delta H is what we call enthalpy. And a lot of the things in thermochemistry, and that's where we're at right now is thermochemistry, sound the same, and we'll get to another one here in a minute. But enthalpy is heat. So when you think of heat, think of enthalpy, delta H. When energy is absorbed, it's said to be endothermic, and delta H is positive. That means I'm putting it in on the reactant side. When energy is released, it's said to be exothermic, so releasing energy, exiting the system, exothermic. And delta H is negative, or it's found on the product side of a reactant. So when we cleave the bond, we have to add energy. It's endothermic. It would be on the reactant side is where I would add that energy. To form the bond, I would put that on the product side because it's a minus, and it's exothermic. Okay, well, while we're waiting for people to get this written down, from this point on, since we're a smaller group, I would like everybody to either sit in the red or the green, because we're going to be doing rotations between red and green, and that way you don't have to turn around trying to watch the board and crank your neck. Okay, so after we do this, I'm going to have you guys that are in the blue move into the green or the red, so that we can do rotations. Okay. All right, going forward, everybody okay? This is really having issues today. All right, so when we're talking about energy change, when you put energy into something, it's going to move it up. And so the potential energy is going to be higher. So when we have bond dissociation energy, or delta H, the amount of energy that we have to put in to break that bond is positive. We have to put energy into it to break them apart and get them. It's like I said, like a divorce. You have to break them apart. They have to now have their own households that are now supporting, so we need more energy or more funds to put that in. When a bond formation always is negative, if you look on the right-hand side, exothermic, it now is lower in energy than it was originally, because now instead of supporting two households, we now are all in one household, and we only have one household expense. So it releases the energy. So I'm saying the same thing over and over again. I'm hoping that it gets to you in one way or another, visually or otherwise. This one that's been on this one is hydrogen bond breaking. You'll see that it actually took more energy to break per mole than the chlorine did, because the chlorine was only 58, but the hydrogen is 104. Now, if you think about it, hydrogen is closer to the nucleus, so that's where our increased energy comes from. Okay, so changes in reaction. Stronger the bond, the higher the bond dissociation energy. Okay, so if you have a really good marriage, to break it apart, it's going to take a lot of energy and a lot of strife to break it apart. If you have a weak marriage, just one thing you left is, whatever, can break it apart. In comparing bonds that form between elements in the same group, the energy dissociation generally decreases going down a column. And if you think about that, at the top of the column, it's really close to the nucleus. So the bonds are really close, okay, to each other's nucleus. And because of that, they're really close. Think about a marriage. If two people are really close, they're sharing things all the time, and it becomes really strong. As you go down that column, the molecules themselves get bigger and bigger, and so the bond now is out here on the very edge of this big molecule, and they're not interacting very much. So in a marriage, it would be, they might say hi or bye as they go to work. Okay, so it's very easy to break that bond. And you can see the difference in the bond energy from 136 down to 71 just in this halogens, which are very wanting to keep their bonds together. Okay. All right, so changes in a reaction. Delta H, remember, relative strength of the bond. If it's a high delta H, you're going to have a very big or strong bond. When it's negative, it's released. So in this reaction, this 213 could actually be added to the product side. So I could say CO2 plus 2H2O plus 213 kilocalories. So they don't have to write delta H off by itself. It could be part of the equation. And it can be treated stoichiometrically as part of the equation too. So I can find out how much heat is given off when I add 435 grams of methane. I can see how much heat that would produce. So this is what they use in furnaces, okay? How they do that. I can also find out if delta H is positive. This would be the making glucose or what plants do, making chlorophyll and glucose. I can put that 678 kilocalories on the reactant side with the CO2 and the water and make it go this way. And it can be part of that equation, and I actually do stoichiometric stuff with that. Okay? If it's broken, I have to put it on the reactant side. If it is formed, I put it on the product side. Positive, reactant. Negative, product. Okay? Come on. Okay, so overall, this is what's going on. So this is sort of a summary page for this. So endothermic reactions, heat is absorbed. Delta H is positive. Bonds are broken in the reactants and are stronger than the bonds that are formed in the products. The products are higher in energy than the reactants. For an exothermic reaction, heat is released. Delta H is negative. The bonds formed in the product are stronger than the bonds formed in the reactant. And the products are lower in energy than the reactants. Come on. It's like it's freezing or something. It must be relating to the hall. Come on. Microsoft is not responding. Sorry guys, computer problems always are fun. We'll just work with it. Okay, so we're going to watch a little video that has to do, maybe, come on.